So hello Year 10 and welcome to the start of a new topic. So far this year you've been looking at very fact-heavy courses. So C7 Organic Chemistry, C2 Structure and Bonding and C8 Chemical Analysis. All of these have required quite a heavy leaning towards learning the facts and making sure you get the right keywords in the right places. We're swinging now completely to the other side of the spectrum. And C3, this topic on quantitative chemistry, is all about concepts and making sure you understand the theories behind what you're doing. In fact, the less rote learning you can do on this topic, the better, because you need to understand what you're doing rather than just learning how to do it. So the first lesson starts quite simply with the idea of conservation of mass, and this is something that shouldn't be new to you. But tied into that are these two key questions. What is the law of conservation of mass? And why do we balance a chemical equation? And these two ideas are linked together. First thing to do is just remind ourselves what a chemical formula actually is. So here are several chemicals. All of them has a formula. So what is the formula for each of these chemicals? If you're not immediately sure, pause the video and have a think before going on again. Hopefully this didn't prove too much of a challenge. There's 2 hydrogen atoms, H2, 2 chlorine atoms, Cl2, and so on for oxygen, for nitrogen. Here there's 1 carbon and 2 oxygens, CO2. 1 aluminium, 3 chlorines, AlCl3. 1 nitrogen, 3 hydrogens, NH3. 2 aluminiums, 3 oxygens, Al2O3. And 1 oxygen, 2 hydrogens, H2O. And hopefully you should recognise this as carbon dioxide. You should recognise this as ammonia, and you should recognise this as water. Now the conservation of mass idea came from a chemist called Antoine Lavoisier. He was an old school chemist who liked to do all of his own experiments. He wasn't classically trained, he was a bit of an amateur. But he worked out that mass is neither created nor destroyed during chemical processes. Mass is always conserved. To get you in the right frame of mind thinking about this lesson, here are 3 demonstrations that we would normally have done in the lab with you, but we've done and recorded for your delight and delectation. Enjoy the video. So hello Year 10s. And as you know, we're looking at conservation of mass and whether or not reactions appear to gain or lose mass. So the first reaction here, what we've got is we've got a balance that is almost perfectly balanced with some iron wool in the container on the right hand side. And the first thing we're going to do is we're going to set fire to that iron wool and see what happens. What do you think is going to happen to this balance? Okay, and you can see here we've got the iron wool that Miss Richardson is about to light. Okay, cool. And if we just watch that now, as that iron wool burns. It's burning nicely. Still burning.
Yeah, still going.
Still going. Is this going to work? Have I set this up correctly? There we go.
And it's moving.
And there we go. So we've got the iron wool gaining mass as it burns. Was that what you expected? Many Year 10 students are surprised by that observation. Can you explain why the iron got heavier as it burnt? Okay, moving on to the next reaction. We have here some potassium iodide and some lead nitrate. So let's zero the balance, Miss Richardson.
Lovely.
Excellent. Zero there. Yeah, about 50 ml of potassium iodide in that. And if you could stick that and the lead nitrate bottle on the balance, and we'll see what the mass is. Okay. Total mass 197.26 grams. And now a few generous squirts of the lead nitrate into that. Now, lead nitrate is, of course, deeply poisonous. You can see the poisonous symbol on there. And here we go. 197.24. That's slightly off, isn't it, sir? But actually showing that we've got this beautiful colour change by reacting those two things together, and virtually no change in mass. Finally, we've got a lovely reaction here, which is very, very strange. It's an odd reaction that we go into in a lot more detail. And the first thing Mr. Reeves is going to do is he's wetting a wooden block here. That's going to go on the balance. And then if you stick the two beakers onto the wood as well, just so we can weigh them.
I've kept the glass rod.
Yeah. 196.68. Okay, now here's the weird thing. We're going to mix those two solids together, and then Miss Richardson's going to give them a good stir, and then put them back on the wood. So mixing them together. Now this is a really odd reaction for three reasons, one of which is it is a solid reaction. So you don't get many of those where actually the reaction occurs between two solids. Or normally you need one of the reactants to be at least in a liquid or a gas. Now, what are you smelling there, Miss Richardson?
I'm smelling ammonia, which is quite a strong smell. It gets to the back of your throat.
Yeah.
And this is very cold.
Yeah, it's getting very, very, very cold here. So that's the second thing that's weird about this.
You can see it's like a form of paste.
So forming a nice paste. Oh, it really reeks, stinks very, very much here now.
And now it's much more liquidy.
Yeah.
Very, very cold to the touch.
It's gone all liquid, not because it's melted, because it's gone the other way round. It's actually got cold. So let's have a look at what's going on here. We'll speed this up in post-production.
Shall I scrape the excess off the glass strip?
I guess in a fume hood this works quite well, doesn't it? Because it's evacuating the ammonia. Cool, so we can definitely see the reaction losing mass there. As Miss Richardson said, these two solids have turned into a paste. And now, do you reckon that's long enough, Mr. Reeves? Okay. We'll see if we take off that and we try lifting the other beaker. What happens, Miss Richardson? There you go. It's cold enough to have frozen the beaker to the wooden block.
It's really cold.
It is well under 0 degrees now, and so that is a reaction. Not only has two solids reacted together to form a liquid, not only has it got cold, but it has also lost mass. Thank you very much, Miss Richardson and Mr. Reeves. Okay, this was one of those reactions. The reaction between potassium iodide solution and lead nitrate solution. Now both of these were colourless. But what observations in this reaction suggested there was a chemical reaction? Well, hopefully you remember some of the things that suggest a chemical reaction, one of which is a colour change. Although potassium nitrate is also colourless, lead iodide is a beautiful bright yellow colour. And you learnt back last year that colour changes were one indication of chemical reactions. This one's a bit more complicated. Explain why the products have the same mass as the reactants. If you got this question in an exam, what would you say? Why do the products have the same mass as the reactants? Well, hopefully you would say something like, no atoms enter or leave the beaker. All of the atoms that were there at the start are there at the end. Look, we've got 2 potassiums. Just notice this isn't balanced. So we've got 2 potassiums, 2 potassiums, 2 iodides, 2 iodides, 1 lead, 1 lead, 2 nitrogens, 2 nitrogens, 6 oxygens, 6 oxygens. So all the atoms that were there at the start in the beaker are there at the end. And that's why the products have the same mass as the reactants. Heating iron wool. This is a lovely experiment, and perhaps you didn't expect the iron to get heavier during this reaction. What observations suggested there was a chemical reaction? Well, heat given out, flames and sparks, there was a colour change again, the sort of lighter grey iron wool became a much blacker colour towards the end, and hopefully again you remember that these are indications of a chemical reaction. Explain why the reaction appears to gain mass. Why did it appear that the reactants weighed less than the products? Well, here we need to carefully look at the state symbols, and we can see that one of the reactants is a gas. And therefore it's not weighed. So the oxygen not weighed at the start. We weren't weighing all of the reactants. And so when the oxygen combines with the iron and the balance goes down, it appears that we have gained mass in this reaction. We haven't. We're now just weighing the mass of the oxygen as well at the end. The opposite idea is this reaction. Barium hydroxide and ammonium chloride. We'll give 2 reasons why this is a very unusual reaction. Well, firstly, look at this. It's 2 solids reacting together. At room temperature. That's really unusual. Normally you need at least one of them to be a gas or a liquid in order for the reaction to progress, but here 2 solids can react. The other very unusual thing is it got very cold. You'll do a topic later on where you look at reactions that get cold. They're called endothermic reactions, but they're much rarer than the exothermic reactions, the ones that get hot that you're used to. Explain why the reaction appears to lose mass. Well, again, looking at the state symbols, we can see that there is a gas made in the reaction. Why does it appear to lose mass? Well, it appears to lose mass because the ammonia is not weighed at the end. There is the same mass of products as reactants because, again, if you look, there's the same number of atoms in the reactants as the products. It's just that we are weighing all of the reactants, we're not weighing all of the products. So the law of conservation of mass says no atoms are lost or made when new substances are formed during chemical reactions. The total mass of the reactants is always equal to the total mass of the products. So if we react copper sulfate and magnesium and it starts off at 11.88 grams and we end up with copper and magnesium sulfate, that will still weigh 11.88 grams. The atoms have rearranged, but they haven't gone anywhere and no new atoms have entered the reaction mixture. Occasionally, a chemical reaction will appear to lose or gain mass. So here's magnesium hydrochloric acid, starting off at 11.8 grams, ending up at 7.8 grams. Why? Well, in this case, we are giving off a gas. In reactions where a gas is given off, the mass of the chemicals in the flask will decrease because gas atoms leave the flask. We're not weighing them. If we were to carry out this reaction in a sealed container, then none of the hydrogen would be able to escape from this reaction and we would see the same mass at the end of the reaction that we had at the start. So, on the left-hand side, gas being given off, so the mass of chemicals in the flask decreases. We haven't lost mass, we're just not weighing it anymore. But if we carry out that same reaction in a sealed container, there's no change in mass. We're going to start quite simply with this bit of maths. Calcium carbonate and sulfuric acid makes calcium sulfate plus water plus carbon dioxide. This is a reaction you should be familiar with from year 8. If I have 20 grams of calcium carbonate and react this with 25 grams of sulfuric acid, and I make 32 grams of calcium sulfate and 3 grams of water, what's my mass of carbon dioxide? Well, the reactants weighed 45 grams. So the products must also weigh 45 grams. Same number of atoms in the reactants and the products. So 32 plus 3 plus X must equal 45 grams. So what is X? Well, X is 45 minus 35. In other words, 10 grams of carbon dioxide must be made in this reaction. Here's another couple of examples. See if you can work out the answers. Pause the video, see if you are right. 100 grams of calcium carbonate decomposes and forms calcium oxide and carbon dioxide. If 56 grams of calcium oxide was formed, how much carbon dioxide was formed? So calcium carbonate forming calcium oxide plus carbon dioxide. 100 grams of this forms 56 grams of this. Well, the products must sum up to 100 grams, because the reactants did, and therefore the mass of carbon dioxide must be 44 grams. 16 grams of copper oxide was formed from 12.8 grams of copper. What mass of oxygen was gained from the air? So copper plus oxygen forming copper oxide. Let's balance it. So we had 16 grams of copper oxide, 12.8 grams of copper. Well, we know the reactants must equal 16 grams because the products are 16 grams. So therefore, the amount of oxygen we need is 16 minus 12.8, 3.2 grams of oxygen. 12.8 grams of copper reacts with 3.2 grams of oxygen to make 16 grams of copper oxide. How about this? How much water do we make? Hopefully you very quickly realised 25 grams. Why? The reactants add up to 25 grams. The products must be 25 grams. How much oxygen is needed in this reaction? Well, hopefully you realised that because the products weigh 50 grams, the reactants must add up to 50 grams. So therefore we needed 30 grams of oxygen. In this reaction, 20 grams of methane, 40 grams of oxygen makes 45 grams of carbon dioxide and water. But what is the mass of water? Well, reactants sum up to 60 grams. Products must also sum up to 60 grams. If the carbon dioxide is 45 grams, we must make 15 grams of water. "100 grams of methane and how much oxygen makes 110 grams of carbon dioxide and 40 grams of water. Products add up to 150 grams. Reactants must add up to 150 grams, so 50 grams of oxygen is needed. And finally, 300 tonnes of iron oxide is reacted with 75 tonnes of carbon. This produces 140 tonnes of carbon dioxide and iron. But what mass of iron is made? Well, our reactants sum up to 375 tonnes. Our products must sum up, therefore, to 375 tonnes. 375 minus 140 equals 235 tonnes. So the amount of iron, 235 tonnes. As I said, the idea of conservation of mass is very tightly linked to the reason that we balance a chemical equation. So consider this reaction, hydrogen reacting with oxygen to form water. Well, which way would the seesaw tilt and why? If we actually had a seesaw that was sensitive enough to actually weigh atoms, which way would the seesaw tilt? Well, hopefully you realise it would tilt to the right-hand side. Why would it do that? Well, we've got more atoms on the right-hand side. We've got 2 oxygens on each side, but we've got 4 hydrogens on the right, only 2 hydrogens on the left. If we throw on another hydrogen molecule on the left-hand side of the seesaw, then it will tilt back the other way. And now it is balanced. We have the same number of atoms and the same type of each atom on the left and the right. That is, 2 oxygens on each side, 4 hydrogens on each side. And this comes from the conservation of mass. In a chemical reaction, atoms will rearrange, but none are created or destroyed. So in a chemical reaction, atoms will rearrange, but none are created or destroyed. Why do chemists care? Why do they want to balance the equations? Why bother? So what if it agrees with the law of conservation of mass? Why do we care? Well, this allows us to work out the amount of product we're going to make. If we follow the conservation of mass and balance the equation, we know how much product, of our desired product, we're going to make from a certain mass of reactants. We need to know the ratio of the reactants that we use. What ratio do we need to mix them in to get the product that we want? We can work out if there's going to be side products that are going to be wasted, and if so, how much mass is going to be wasted. And we can also use these to start thinking about whether other reactions are likely or could take place. There's two common methods used to balance chemical equations. And particularly in C7, you will just be given the word equation because it is assumed that you know the formula of ethane. Eth, 2 carbons. It's an alkane, so we have twice as many plus 2 hydrogens, C2H6. You should know that oxygen is diatomic. You are expected to know the formula of carbon dioxide and water. Once we've got that, the first method involves a tally. So we've got carbon, hydrogen and oxygen on the left hand side, carbon, hydrogen and oxygen on the right hand side. So at the moment we've got 2 carbons, 1 carbon, 6 hydrogens, 2 hydrogens, 2 oxygens, 3 oxygens. With combustion equations, remember, think Harry Potter and Cho Chang. Balance the carbons, then the hydrogens, then the oxygens. That's Mr. Slater's method. So, balancing the carbons, well, how can we get 2 carbons? Well, if we have 2 carbon dioxides, well, what does that change? That now means we've got 2 of those, and it now means that we've got 5 oxygens. So the carbons are okay. Hydrogens. Okay, we've got 6 on the left, we've only got 2 on the right. Well, if I make that 3, what does that change? Well, now I've got 6 hydrogens on the left, which is good. But now I've got 3, 4, 5, 6, 7 oxygens on the right hand side. What do I need here? Well, I need 5 more oxygens. 5 more. So I need to add another 2.5 O2, making 3.5 in total. That would give me 7. And everything would be good at that point. But we don't like the half. We're not happy with the half. So what can we do? Well, what we can do is we can double everything. If I times all of these by 2, so I've got 2 of those, and 7 of those, and 4 of those, and 6 of those, so doubled all my numbers. Well, now I've got 4 carbons on the left, I've got 12 hydrogens on the left, I've got 14 oxygens on the left, I've got 4 carbons on the right hand side, I've got 12 hydrogens on the right hand side, and I've got 8 plus 6, 14 oxygens on the right hand side. That is all balanced. Perfect. The other method that people sometimes use, particularly if they tend to make a lot of mistakes in the first method, is to draw out all of the atoms. So ethane, C2H6, so 2 carbons, 6 hydrogens. It doesn't matter if you know what the molecule looks like or not, as long as it's got the correct number of each atom. So we've got O2, CO2 and H2O. Well, again we're going to balance using Cho-Chang. So 2 carbons, so we need 2 carbons on the right hand side. But I can't just add a carbon. I have to add a whole molecule. There isn't any carbon in this equation, so we can't just add a single carbon. In the same way we can't add a single oxygen or a hydrogen molecule. It's not there in the reaction. So if we want to add another carbon, it comes with its mates. It comes with the 2 oxygens. Next for the hydrogens. Well, there's 6 over here, so we need another 4 on the right hand side. But again, the hydrogens only come with the oxygens, so we have to add another couple of waters. We've got 7 oxygens on the left hand side, so we need another couple of these, that's 6, and we need another oxygen, but we can't do that. Oxygen doesn't come singly, it only comes in pairs. What we actually need is half an O2 molecule. But we can't have half an O2 molecule. Again, this is where we have to double the reaction. So we would say to ourselves, okay, well, what happens if I start off with 2 ethane molecules instead? Well, now we've got 4 carbons on the left, so we would need another couple of carbon dioxide molecules on the right hand side. We've now got 12 hydrogens on the left, so we need another 3 water molecules on the right hand side. Now we've got 8, 9, 10, 11, 12, 13, 14 oxygens, which is good because that's 7 pairs. So that is your oxygen pair there. That's 8, 10, 12, 14. We've got 4 carbons on the left, 4 on the right. 12 hydrogens on the left, 12 hydrogens on the right, 14 oxygens on the left, 14 oxygens on the right. It's more time consuming this way, but actually you're less likely to make a mistake. It's up to you how you want to balance the equations, as long as you use a method that works for you, and unless you're getting it right every time, I strongly advise that you show you're working and either use the tally method we saw here, or you use the draw it out method from here. So for the rest of the hour, go to Google Classroom, have a look at the worksheet and see how many equations you can balance in the remaining time of this lesson. Any problems? Email me or Miss Watts. Over to you.